Okay, let's see if we can get this to work. I think this is okay. I want to do a review of rotational unbalance because the day I gave that lecture, I felt it wasn't really adequate. So we're going to redo some of those notes so that they are on record for you to follow. And before I jump into shut my phone, into the details about this problem with the rotational unbalance, I want to talk about a general idea of internal forces. So let's say I have some weird looking mass that looks something like this. This is some big mass. I'll call it M total. And if I were to draw a free body diagram of M total, let's say, there's gravity acting in this problem. My free body diagram would be, okay, I have M total times G pointing down. And because of the ground is going to cause a normal force to act on the entire mass. Nothing groundbreaking here. But instead of having this, let's assume I now have a mass, I'll call it M1, and on top of it is a mass M2. And I want to draw a free body diagram of each of these guys individually on the ground. So if we look at M2, this is M2. I basically have just taken this guy and I'm just examining the forces that are acting on that one mass. I'm going to have M2G that's pointing down, and I'm going to have some sort of reaction force due to the fact it's on top of the mass because the mass is going to push up on it. So I'm going to say that there's some reaction force. I'll call it R. Cool. Let's do the same thing with M1, which is the bigger mass and it's below. This is going to have M1G going down. The Earth is going to apply some normal force to it. And in order to take into account the second mass, we have to include the fact that a reaction force that is caused by M1 on M2, that reaction force is going to be equal and opposite because of the effect that M2 has on M1. So that means that there's going to be an R pointing down. So I'll say that one more time. So M2, because it's on top of M1, will feel some sort of reaction force because of the fact that it's in contact with M1. But M1 will also feel some sort of reaction force because of M2 on top of it. And I'm writing that reaction force as R. And that's great. Those are their individual free body diagrams. If I combine them, let's add up all our forces. So we see that we have an M2G and M1G pointing down. So maybe I'll say M1 plus M2G. I have this normal force N that's pointing up. And if you look, this R and this R are equal and opposite, which means that they do not play a role in the final free body diagram. And that R is what we will call some sort of internal force that if you looked at the system as individual parts, you'd see that there's some internal force that exists. But when you combine them and then you're just looking at it from an outside perspective, then that means that we have only the forces that are acting along with the Earth, basically, at the ground. Those reaction forces don't play a role if you're looking at it as a whole system. And this type of thing is leveraged when we do rotating unbalance. So let's draw a picture for rotational unbalance. And it's going to be from note set 11, right? This is note set number 11, if you want to follow along. So in note set number 11, the way that I drew this drawing is I have some sort of rectangle. It is on top of a spring and a damper. This is K, this is C. This thing's gonna be able to move up and down in X. And inside of this guy, maybe I will make it a little bit bigger. You can draw it better. Inside of this dude is a point mass here that is some distance away that we call E, and it is rotating around omega RT, right? Omega R is a frequency. That's going to be something like radians per second. And then T is in seconds. So if we do omega R times T, we have radians per second times seconds. That's just going to give us radians. So omega RT is an angle, basically telling us the position of the rotating unbalance. So as this thing oscillates, in a circular path, it is going to create a force on the mass that is going to cause it to move up and down. And that's the whole point of rotating unbalance, is that this uneven distribution of mass is going to cause some fluctuations or some vibration that we, in a lot of cases, want to avoid. In some cases, you might want to leverage it. But we're going to try to just understand its behavior. So let's go ahead and look at the different parts of the system. So first off, we have the whole system. I'm going to say, actually, I'll just remove the M for now. I'm going to say that this is the whole system. And that is equal to some M. This is the total mass. Now let's say I just look at the box without the mass. And we'll also look at just the mass. So just the mass is m naught. We know the mass of that object, that point mass. If this is the rest of the box, and this is, let's say, a hole, we're not including that point mass in this. I call this in the notes m rest, which is basically saying the rest of the mass. That's going to end up being m minus m naught. The total mass minus the point mass gives us the rest of the mass of our machine or of our system. So let's look at these two, subcomponents, kind of like our two blocks in that previous example I did on top of each other. Let's look at them separately. So let's look at first, and I think in the notes, I look at the point mass first. So we'll look at the point mass first. So the point mass, is some distance away from the center. We call that the eccentricity, or E. And the angle that it makes is omega R times T. Like we just said, that's an angle. And if you think about the position of this mass, remember that this whole system here is going up and down. So there's translational motion. Of the whole system. And then the point mass is also oscillating around in a circle, because the machine is spinning or something. So we also have this rotational motion of the point mass. So that means we need to take this into account to figure out where this mass is. So we're looking for where is the position of m naught, x of m naught. What is that? And that's going to be a function of time. Well, it's going to be based on the translational mass. Imagine it wasn't rotating. Its position would just be based on where the big mass is, up and down. So x m naught of t, that's equal to x of t. That's what we're trying to understand, is the motion of that. That is our translational motion. This is x of t. Right, we see that up here. That's the up and down motion of the whole system. And then we also have this rotational motion that's occurring. And I think I call this in the notes xr of t for rotation. And since this thing is only allowed to move, up and down, we're saying it's on some sort of roller or something, and it's only able to move up and down. It can't go left and right. The only thing we care about in regards to its position is in the vertical direction. So this is going to be plus xr of t. X of t we don't know, but the position in the vertical direction for its rotation we kind of do know, because we know how far away it is. It's e. And what we want to find is this distance here. This is xr of t. Remember, it's spinning around, and its position relative to the center of the box, which is where its central axis is, its axis of rotation is, it's going to be based on, this is omega rt, it's going to be based on the sine of that angle. So it's going to be sine of omega rt is opposite over hypotenuse. So sine omega rt is xr of t over e. Therefore, that this xrt ends up just being e times sine omega rt. We'll double check that. Yeah, okay. So that's the position of this mass. We have the position of little m naught. We'll just save that for now, because we're going to come back here and do a free body diagram in a second, but I'd rather look at the other system first. So we'll look at m rest, which again was the system without the mass. And that was on a spring and the damper and stuff. So let's draw a free body diagram for this guy and see what forces are present. So first off, we have some spring force. If the mass goes up, the spring force is going to try to pull it back down. And same thing with the damper. The damper is going to try to slow it down. It's based on the velocity, and it will also point in the opposite direction of the motion. Now, because we're looking at a subsystem here, kind of like this problem. In this problem, I'm looking at a subsystem of this whole giant mass thing, and I have this reaction force present because of the fact that the small mass is in contact with the big mass in this problem. That same type of thing occurs here, because as the little mass is rotating around, it is applying a force to this block. And that is what we're saying is FR. I think I do lowercase r. Yeah, lowercase r. FR. So depending on the properties of the point mass, how big it is, how far away it is, that'll exert a certain force on the rest of this mass. Again, this is m rest. So we can do the sum of forces for this problem. And that's going to be equal to m rest, because I'm just looking at the rest of the system. I'm not looking at the whole system. I'm just looking at this without the mass, times its acceleration, which is x double dot. So I have FR pointing up. I have KX pointing down. I have CX dot pointing down. And m rest, remember, was the total mass, m minus m naught. This is m minus m naught x double dot. That's pretty good to have for now, but the one problem is we do not have F sub r. We don't have the reaction force that occurs because of the point mass oscillating. So let's go back to this picture here. And we have this point mass. We're neglecting gravity in this problem. So if we were to draw a free body diagram like this, we're just going to ignore the point mass. The point mass is weight. The question is, what forces are acting on it? Well, similar to the little mass and the big mass in that initial problem, there has to be some sort of reaction force acting on this little mass because of the reaction force that it is exerting on the rest of the system. And a way to think about this is you have point mass causing reaction on m rest, and in response, m rest is going to cause a reaction on the point mass. Because of Newton's third law, you have equal and opposite reactions. If we come back to this, that means that we have some force FR that is going down. And that's it. There's no other forces acting on this mass if we're neglecting gravity. So we're going to sum the forces for this mass. And that's going to be m naught, just its mass, which is the point mass, times its rotation, or its position, I mean rather, x double dot of the point mass. So if we plug in the second derivative, which is based on this equation here, we'll get x double dot. The first derivative is e omega cosine. The second derivative is e omega squared with a negative sign. So it's minus e omega r squared sine omega rt, I think. I guess I don't even need that yet. You know what? Maybe just for the sake of keeping the algebra cleaner, I'll try this as xr of t double dot. This equation. The second derivative of that is x double dot plus xr double dot. If I get rid of the t just for simplicity. So the only forces that are acting on the system, and again, we're assuming it's going up, will be the negative force of the reaction, right? This is going to be negative f sub r. This is equal to m naught x double dot plus x double dot r. So now I know what fr is. Fr is going to be negative m naught x double dot plus x double dot r. That's my reaction force. And now I can take this and I can substitute it into my other equation. And I know I might be going a little fast here, but go ahead and pause it if you want to look back at some of the things that I've written. So coming to this equation, which I'll rewrite on the next slide, it's fr minus kx minus cx dot. That is equal to m minus m naught x double dot. Double check that I did that right. M minus m naught x double dot. Negative spring force, negative damping, fr going up. That seems right. So if we plug in what fr is, fr was negative m naught x double dot plus x double dot r minus kx minus cx dot. That is equal to m minus m naught x double dot. And just a reminder, m is the total mass of the system, including the point mass. M naught is the point mass itself, and this mass that we have here, that quantity, m minus m naught, is the rest of the system. That's our subcomponent. So if we go ahead and distribute, we get negative m naught x double dot minus m naught x double dot r minus kx minus cx dot. If I distribute the last guy, that's mx double dot minus m naught x double dot. And now I can look at both sides. So we see that I have a negative m naught x double dot there and a negative m naught x double dot there. That will cancel. So I have an m naught x double dot r, spring, and a damper. Those are all negative at the moment. So what I'm going to do, just to get into a form we're familiar with, is that I'll bring the kx and the cx dot over the other side with mx double dot. So that'll give me mx double dot plus the damping force plus the spring force. That'll be equal to negative m naught x double dot of r. Write down what x of r is again. That was e sine omega rt. And I already mentioned this before, but I'll do it just to be thorough. If I take the derivative of this, an omega r will come out. And if I take the second derivative, another omega r will come out. So I don't know if my face is in the way. I see like a little picture of my face. Another omega r is going to come out and end up being negative. So negative e omega r squared and omega rt. We'll plug that in to right there, and we'll see that the negative signs cancel. So you get mx double dot cx dot plus kx. That is equal to m naught e omega r squared sine rt. And if you look, this guy right here is some quantity in front of sine omega rt. That means that that is equivalent basically to our capital F naught. That is the amplitude of our force. And that is what we've seen a lot in this class previously. That occurs because of the rotating unbalance. So let me see if there's anything else I want to talk about here besides just deriving it. I'm not going to talk about solving it because that's in the notes and we went over it in class and it's, not really necessary. But at the end of the day, if you were to solve it, you'd end up having a deflection that looks like x of t is m naught e over m times r squared, which again is the frequency ratio, the square root of 1 minus r squared squared plus 2 zeta r squared sine of omega rt minus the arctan zeta r minus 1 over 1 minus r squared. So this guy here, this is the amplitude. Our displacement, because that's the max that it could possibly be. If sine is 1, then that means that will be our max displacement. And we see that if m naught or e go up, we have an increase of amplitude. If the total mass goes up, that decreases amplitude. And I think the example I used in class is that if you have a rotating system that's 1 million pounds and a fly lands on it, well, relative to the total mass, that little m naught's going to have very, very, barely any impact on the system. And that's what that equation shows us. So I hope this was helpful from a derivation standpoint. If you have more questions, let me know. And please, I encourage you to look at the notes and do your homework. And, again, come let me know if you have questions about this. Thanks.